Hello everyone. Today we are going to learn about matrix representation of graphs. Although representation of graphs by diagram is very convenient for a visual study, it may not be suitable to store a large graph in a computer. The matrix is a convenient and useful way of representing a graph to a computer. The advantage of matrix representation of graphs is many results of matrix algebra can be applied to study the structural properties of graphs. In this module, we shall discuss two most commonly used matrix representation of a graph, adjacency matrix and incidence matrix. First, we shall learn the definition of adjacency matrix. Definition: let G be a graph of order n and size m. Let V of G is a set of all vertices consisting of V1, V2, etc. Vn, and E of G is a set of all edges consisting of E1, E2, etc. Em. The adjacency matrix of G is the n by n matrix A, matrix Aij, where Aij is equal to 1 if Vi, Vj belong to E of G and that is equal to 0 otherwise. Some observations regarding the adjacency matrix are: the adjacency matrix A is a symmetric n by n matrix. Second observation is every entry along the principal diagonal of A is 0. Third one is in A the number of ones in row I or in column I is the degree of the vertex Vi. And the fourth one, two graphs are isomorphic if and only if their corresponding adjacency matrices differ only by a permutation of rows and columns. The next one is if G is a graph with n vertices V1, V2, etc. Vn, and let A denote the adjacency matrix of G with respect to this listing of the vertices, let B be the matrix B is equal to A plus A square plus A cube, etc. plus A power n minus 1, then G is a connected graph if B has no 0 entries for the main diagonal. Now, let us see examples of adjacency matrix. Now, we have seen the definition of adjacency matrix. Let us see some examples regarding adjacency matrix. So, here we are going to see two examples. The first one, we are going to represent this graph in adjacency matrix, and the second one, we are going to find the graph associated with this adjacency matrix. Let us look the first one. So, this is a graph given to us. We are going to find the adjacency matrix associated with this graph. So, as you can see here, there are 6 vertices V1, V2, V3, V4, V5, V6. From the observations, we can say the adjacency matrix will be a square matrix of order 6, that is, it will be a 6 by 6 matrix. So, the rows and columns of the adjacency matrix corresponds to the vertices V1, V2, V3, V4, V5 and V6. So, we are going to find the entries of the first row. As you can see here, V1 is not adjacent to V1, that is, this is a simple graph, there is no loop in here, which means the entry in the first row, that is V1 is 0. Similarly, V1 is not adjacent to V2, therefore the second entry is also 0, and V1 is not adjacent to V3 and the third entry in the first row is also 0. V1 is adjacent to V4, therefore we are going to give 1 for the fourth entry in the first row, that is V1, V4 entry is 1, and V1 is adjacent to V5, therefore we are going to give 1 for the fifth entry in the first row also. V1 is not adjacent to V6, therefore we are going to give 0 for the last entry in the first row. Similarly, we can give all the entries for the rest of the rows. So, here V4 is not adjacent to V4, therefore we are giving 0 for this entry, and V4 is adjacent to V5, therefore we are giving 1 to this entry, that is 4th row and 5th column, that is V4, V5 is 1. So, in similar way we can represent a graph via matrix. So, this is the best relation that applied to graph theory as well as in algebra. We can relate graph as well as algebra. So, in the second example, we are going to find a graph associated with this adjacency matrix. So, this is a 4 by 4 square matrix. The vertices are labeled as A, B, C, D. So, there are 4 vertices here and we are going to find the corresponding graph of this adjacency matrix. For this, we are going to place all the 4 vertices on a plane. You can place it anywhere. Here I have placed like A, B, C, D. This is our first step. And for the second step, look at the first row here. A is not adjacent to A because the entry in the first row, that is first entry is 0, which means A is not adjacent to A. I am not going to give any loop here, but A is adjacent to B as the entry is 1 here. So, I am going to make A and B to be adjacent with each other. And similarly, in the first row, if you can see here, the entry is 1 here, that is A and C are adjacent to each other. So, I am going to make A and C to be adjacent with each other. So, this is step 2. Step 2 I finished with A, that is first row I finished. Coming to the step 3, here, so we already made we already finished A. So, we are going to look the second row here. In the second row, B is adjacent to A. As you can see, 1 is here, that is the entry is 1, which means B is adjacent to A. But here we already made A and B to be adjacent, no need to do that again. In the second row, B is not adjacent to B, there is no loop here. I am not going to give any loop here to B. And B and C, the entry is 0, which means B and C are not adjacent. I am not going to give any edge, that is any line here. And B and D, the entry is 1. So, B and D are adjacent to each other. So, in the step 3, I made B and D to be adjacent. So, in step 2, A and B and A and C are adjacent. So, we already made A and B to be adjacent, no need to write that again. So, I just made B and D to be adjacent. And coming to step 4, we are going to focus on the third row, that is the vertex C. Here C and A are adjacent because the entry is 1. So, I am checking here C and A are already adjacent, I made already adjacent A and C. So, I am going to leave that, and C and B are not adjacent. So, C and B are not adjacent, C and C are not adjacent, that is because the entry is 0, I am not going to give any loop here. And C and D, the entry is 1, I am going to make C and D to be adjacent. So, this is my step 4, and coming to the step, that is last step, D and A is not adjacent, D and D is not adjacent, D and B is adjacent because the entry is 1, D and B is adjacent here, and D and C, it is also adjacent, that is the entry is 1. So, D and C is already adjacent here, and D and D, the entry is 0, I am not going to give any loop here. So, as you can see here, if we finish up to the third row, we already attained the adjacency matrix. We can use this last entry to just check. So, if it is a 4 by 4 matrix, we finished up to the third row, we will get the entire matrix if it is a simple graph. Okay, so, these two examples tells us we can always associate a graph theory to its algebraic structure. That is, this is a graph we converted in terms of an adjacency matrix, and vice versa also. If adjacency matrix given, we can find its related graph. Now, we shall see the next example. So, this is graph G and this is graph G dash. We are going to show these two graphs are isomorphic to each other by using adjacency matrices. We have seen already that two graphs are isomorphic to each other if their adjacency matrices differ only by the permutation of rows or columns. So, we are going to find first the adjacency matrix of corresponding to this graph G, and we are going to denote that by A of G, and then we are going to find adjacency matrix corresponding to this graph G dash, and we are going to denote that by A of G dash. First, we will find adjacency matrix for corresponding to this graph G. So, here we are having 5 vertices A, B, C, D, E. So, our adjacency matrices will be of order 5 by 5, that is its square matrix of order 5. So, the first entry corresponds to the vertex A. Here A is not adjacent to A, that is there is no loop here. So, the entry is 0, and A and B are adjacent, the entry is 1. A and C are not adjacent, so the entry is 0. A and D are adjacent to each other, so the entry is 1. A and E are not adjacent, so the entry is 0. So the first row got over. Similarly, we can find the entries for all other rows. So this is our adjacency matrix corresponding to this graph G. Similar way, we are going to find adjacency matrices, adjacency matrix corresponding to this graph G dash. So here also we are having 5 vertices A dash, B dash, C dash, D dash and E dash. So it will be a square matrix of order 5. So this is the first row corresponds to the vertex A dash, and the second row B dash, third C dash, fourth D dash and fifth row E dash. So A dash is not adjacent to itself, that is the entry is 0. A dash and B dash are adjacent to each other, the entry is 1. A dash and C dash are not adjacent, the entry is 0. A dash and D dash are adjacent to each other, the entry is 1. A dash and E dash are adjacent to each other, the entry is 1. So we got finished with the first row. Similarly, we can find all the entries for all other rows by the usual procedure. So this is the adjacency matrix corresponding to G dash. As you can see here, so this is the adjacency matrix corresponding to G dash, and this corresponds to G, and we can obtain the same matrix by permuting the rows of this A of G dash. That is, if we permute these rows, we got D dash, A dash, B dash, C dash, E dash, and the corresponding entries I have written here. So you can see these two matrices are one and the same, which means that A of G is equivalent to A of G dash. So in turn it implies my G and G dash are isomorphic to each other. So the isomorphism here is, we are defining a map from G to G dash, where f of A, this f of A I am mapping to D dash, that is f of A is equal to D dash, and similarly f B I am mapping to A dash, that is f of B is equal to A dash. C I am mapping to B dash, f of C is equal to B dash, and f of D is equal to C dash, f of E is equal to E dash. This is the corresponding isomorphism between G and G dash. So we have shown G and G dash are isomorphic to each other by using adjacency matrices. Now we will learn about incidence matrix. We shall see the definition first. Let G be a graph of order n and size m. Let V of G is a set of all vertices, that is V1, V2, etc. Vn, and E of G is a set of all edges, that is E1, E2, etc. Em. The incidence matrix of G is the n by m matrix B, that is matrix Bij, where Bij is equal to 1 if Vi is incident with Vej, and that is equal to 0 otherwise, that is if Vi is not incident with Ej. Some observations regarding the incidence matrix are: the first one, a row with all 0 entries corresponds to an isolated vertex, that is a vertex of degree 0. Second one, a row with a single unit entry corresponds to a pendant vertex, that is a vertex of degree 1. The number of ones in row I of the incidence matrix B is the degree of Vi. In B, the number of ones in each of its columns is 2, since each edge is incident with exactly 2 vertices. If G is connected with n vertices, then the rank of B is n minus 1. Now let's see examples of incidence matrix. As we have seen the definition of incidence matrix, the ijth entry of incidence matrix denoted by Bij, that is equal to 1 if Vi is incident with Ej, 0 otherwise, that is if Vi is not incident with Ej. We shall see examples now. The first example, we are going to represent this graph via incidence matrix. So this is the graph given, we are going to represent this graph in incidence matrix. So the vertices are V1, V2, V3, V4, V5, and the edges are labeled to be E1, E2, E3, E4, E5 and E6. So as we have seen the definition, it's not going to be a square matrix, whereas it's going to be a matrix of order 5 by 6. So it need not always be a square matrix here. So this is the rows corresponds to the vertices, V1, V2, V3, V4, V5, and the columns corresponds to edges E1, E2, E3, E4, E5, E6. Let's focus our attention to the first row. The first row corresponds to V1. Here, look at here V1. So, E1 is incident on V1. So, the first entry here is 1. Similarly, E2 is incident on V1. The second entry is also 1. E3 is incident on V1. The third entry is also 1. So, whereas here E4 is not incident on V1 and E5 is not incident on V1, E6 is not incident on V1, which means that the last 3 entries of the first row becomes 0. Similarly, consider the second row. Second row corresponds to the vertex V2. Here, look at the vertex V2. Here, E1 is incident on V2. So, the entry becomes 1 here, and when you look at E2, E2 is an edge which is not incident on V2, the entry is 0. Similarly, E3 is 0, E4, here E4 is incident on V2, so the entry becomes 1, and E5 and E6 are not incident with V2, so the entries becomes 0 and 0. Similarly, we can find all other entries for the adjacency incident matrix here, and actually we found out this matrix by focusing our attention to the rows. So, similarly we can find this incident matrix by focusing our attention to the columns. For example, if we consider the first column corresponds to the edges E1, as we know that a single edge corresponds to 2, that is incident on 2 vertices V1 and V2. So, here E1 is incident on V1 and V2. So, in the first column only 2 entries will be 1, that is V1 and V2, the rest of the entries are 0. And when you look at the second column corresponds to E2, and E2 is incident on V1 and V3, the corresponding entry, that is the first row first entry, and the third row second entry will become 1, the rest of the entries are 0. Similarly, E3 is incident on V1 and V4, the corresponding entries become 1 here, the rest of the entries are 0. Similarly, we can find the incidence matrix by focusing our attention to the columns. So, here we represented the graph via incidence matrix, and in the next example we are going to represent this, that is we are going to find the graph associated with this incidence matrix. So, here this is the incidence matrix, the order of the incidence matrix is 5 by 6, and we know that the rows corresponds to the vertices and the columns corresponds to the edges, which means that we are having 5 vertices and 6 edges. So, we have here 5 vertices and 6 edges. So, what I am going to do is I am going to place all the 5 vertices on a plane, that is V1, V2, V3, V4, V5, and I am going to check the entries for the columns, that is E1, E2, E3, E4, E5, E6. So, now we placed all the vertices on a plane. Look at the first column E1. Here E1 is incident with V1 and V4. So, here E1 is an edge that connects V1 and V4. So, I am going to connect V1 and V4 by using the edge E1, and let us focus our attention to the second column. Second column corresponds to E2. E2 is adjacent with incident with V1 and V5. So, V1 and V5 are adjacent via the edge E2, and the third column E3. E3 is incident on V2 and V4, that is V2 and V4 are adjacent to each other via E3. Similarly, E4 is incident on V2 and V5. So, V2 and V5 are adjacent via E4. E5 is incident on V3 and V5, which means that V3 and V5 are adjacent with an edge E5. E6, this is the last column. So, E6 is incident on V2 and V3. V2 and V3 are adjacent to each other through the edge E6. So, from here we already converted this incidence matrix to a graph. This is the graph associated with this incidence matrix. We can see here this is a graph consisting of 5 vertices and 6 edges. The order of the incidence matrix is 5 by 6. Now, we shall see a theorem based on isomorphism of two graphs. Theorem 1, the statement is, two graphs G1 and G2 are isomorphic if and only if their incidence matrices differ only by permutation of rows and columns. We shall see the proof now. Let the graphs G1 and G2 be isomorphic. Then there is a 1:1 correspondence between the vertices and edges in G1 and G2 such that the incidence relation is preserved. Thus, B of G1 and B of G2 are either same or differ only by permutation of rows and columns. Conversely, assume that the incidence matrices of G1 and G2 differ only by permutation of any rows or columns. This simply corresponds to relabeling the vertices and edges of the same graph. Thus, G1 and G2 are isomorphic. Now, we shall see a theorem based on the power of an adjacency matrix. That is theorem 2. The statement is, let G be a graph with vertex set V of G that is equal to V1, V2, etc. Vn, and let its corresponding adjacency matrix be A, that is matrix Aij. Then, for any k greater than or equal to 1, the ijth entry of A power k is the number of distinct Vi, Vj walks of length k in G. We shall see the proof now. We prove the result by induction on k. The number of Vi, Vj walks of length 1 is equal to 1 if Vi and Vj are adjacent, and that is equal to 0 otherwise. Hence, that is same as Aij. Hence, the theorem is true for k is equal to 1. Now, assume that the result is true for k minus 1. That is, the number of Vi, Vj walks of length k minus 1 in G is given by Aij power k minus 1, where the matrix A power k minus 1 is the matrix Aij power k minus 1. Now, A k minus 1 into A, that is product of the matrices A k minus 1 into A, is equal to the matrix Aij power k minus 1 multiplied by the matrix Aij. Hence, the ijth entry Aij power k in A power k is the product of ith row of A power k minus 1 and jth column of A, that is Aij power k is same as summation t varies from 1 to n Ait power k minus 1 into Aij. So, every Vi, Vj walk W of length k is produced by beginning with the Vi, Vt walk W dash of length k minus 1 followed by a vertex Vj which is adjacent to Vt. By induction hypothesis, the number of Vi, Vt walks of length k minus 1 is Ait power k minus 1, while Vt is adjacent to Vj if and only if Atj is equal to 1. Hence, Aij power k gives the number of Vi, Vj walks of length k in G. Hence the theorem. The example for the theorem that we discussed now is given in the script. Please refer to that. Now, we shall see a straightforward corollary of theorem 2 regarding distance between vertices. Corollary: let G be a graph with the vertex set V of G is equal to set of all vertices V1, V2, etc. Vn, and let A be its corresponding adjacency matrix. If D of Vi, Vj is equal to x, then Aij power k is equal to 0 for 1 less than or equal to k less than x. Conclusion: in this module, we gave the interrelation between graph structure and algebraic structure. Specifically, we constructed matrices from the given graphs. Hope you all understood the concept of matrix representation of graphs and the use of it. Try to create many more examples and learn about the properties of matrix representation of graphs. Thank you.